before the break, what did we do?
What do we do?
What did we do before the break? Laws of logarithms, right? So properties of logs, separating them, combining them, and change of base. So really just kind of simplifying logarithm expressions. We finish up with exponential logarithm functions today. Solving equations. I'll say the best way to do it is just jump right in. So. Solve 2 to the x equals 6. Generally speaking, when you're dealing with exponential equations, the first thing you want to ask yourself, do they have a common base? And so it's 6 to the power of 2. It's not. Bummer. If it was, then you could just set the exponents equal to each other. How do you undo an exponential? Remember, the goal for solving any equation is you always want to isolate x. So how would you undo an exponential? It's the opposite of an exponential.
Square root.
That'd be if it's a power. It's not power, it's exponential. So it's the inverse of an exponential. What was it?
No, and what?
We just studied it. Inverse of an exponential is a logarithm.
X equals 6 squared.
So take the log of both sides. It honestly doesn't matter what base. You can use any base you want. I'll just use base 2. Right, according to that, log base 2, 2 to the x, it's just x, isn't it? There's your x. write a solution set. Again, 15, not a power base 2. So we take a log, both sides again. Our only exponential is base 2, so I might as well just do log base 2. Log base 2, 2 to the 3x minus 4. The log and the exponential are the same base. So
So
you
it's
just the x.
x minus 4. And then you can subtract 3 minus 4 by both sides.
Subtract 3 minus 4.
I'm sorry. Plus 4 to both sides.
Right? Now that's just a regular linear equation.
Then you can divide it by 3.
There are a few ways that we can write this. We could leave it like that. That's fine. Or we could use our properties to try and write this as a single logarithm.
Like doing the combination thing. Well, here's a division one.
Let's actually do this in a different color. Just to signify all this is optional.
Quotient.
Not right now. First thing, write the 4 in terms of logs. And 4 would be log base 2 of 2 to the 4th. What's 2 to the 4th? And 16 times 15. I'm not going to do that just yet. I think what I'll do is this first. Apply that 1/3. Remember, it's a power. Then the sum law, log of the product, and then simplify it. Two to the 4/3 is the same thing as 2 times 2 to the 1/3, right?
You said 2 to
4/3.
is the same thing as well.
2 times 2 to the 1/3. In other words, cube root of 2 to the 4th, 2 times cube root of 2. Now you have cube root of 2 times cube root of 15. That's just cube root of 2 times 15. And so if you wanted to simplify it to be just a single logarithm, you could also write that.
But we could have just left that at the beginning.
So again, I'm just going to boil down to what looks cleaner. Now, it's possible you're going to be asked to actually write it as a single log, in which case you have to go all the way. Here we have more than one exponential expression, right? Do they have a common base?
No.
No, they don't. Bummer.
But you could.
It doesn't change how we approach it. Other than if they had a common base, we just set the exponents equal to each other and solve. We're still going to wind up taking a log of both sides. How do you undo an exponential? A logarithm. But the question is what base?
5.
Could do base 5.
Or maybe 7 since it's easier.
Could do base 7.
Do 5.
Doesn't matter. You can use any base you want. Because remember, the laws of logarithms, all those properties are valid regardless of the base. I'm just going to use the most commonly used base, E. Microsoft updates it and breaks my computer. Good, I'm installing updates now. Okay, look back. That's the wrong slide though. That's where it was. So we're taking the natural log of both sides. Let's go with that. Okay, now why natural log? No, it's just because that's the best. Like I said, it doesn't matter what base you use. You can use whatever base you want. It'll all work out to be the same. Now it's a matter of isolating x. Use the properties of logarithms. The first property is the power property, the power law. Right. Distribute. Now remember, natural log of 5, natural log of 7, they're just numbers. This is a linear equation now. Move all x terms to one side, move all other terms to the other. Let's keep the x's positive. For this problem then, let's move all the x's over to the right-hand side
Plus X.
and everything else to the left-hand side. So subtract log 7, add x log 5. And remember, equality is transitive. That's actually not the one I wanted to use. Transitive means something else. Equality is transitive. Is that reflexive? It might be. If x equals y, then y equals x. Doesn't matter the order in which you write the equality. Right, so just to make it look the right way, I'll rewrite it reflexively. You can factor out an x from the left-hand side now, right?
We could just divide the whole thing. Is the part before you factored the same thing, it just flipped as the part before that?
Yep. I just use the reflexive property of equality. Just so I can have the x's on the left-hand side. that is our solution. That looks kind of hideous. Again, let's use some properties of logs to see if we can write that as a single logarithm. Five to the fourth power.
The properties of logarithms, you don't mean like the quotient stuff.
Yeah. The laws that we studied before spring break.
Or couldn't we do the quotient one first?
Not yet. And there is no quotient law. It's the difference law.
The laws of logs.
There should be.
The product law, the quotient law.
Oh, is that what they're called? Just remember when it says product law, it doesn't mean product of logs. It means log of the product. So if you're referring to the difference, then yes, but you can't do it yet. Because you don't have a difference of just logs, right? It's 4 times a log. You have to get rid of that 4 first, using the power law. Five to the fourth power, you know what that is?
Five 12.
512 is, what is that, 2 to 9? Yeah, 2 to 9 is 512. Five to the fourth is also 25 squared.
625.
It's 625. Seven cubed. $49 times 7. What's 50 times 7?
Is what?
50 times 7.
For 450. 450.
You're off by 100. It's 350. Now subtract 7.
That's how it works.
Mhm.
Wait.
343.
343. 7 cubed is 343.
Wait. You did 49 times 7.
Yep. 49 times 7 is 343. There are 2 ways you go about it quickly. 40 times 7 plus 9 times 7. Or just go to 50 and then subtract 7 from your result. Because 49 is 50 minus 1. And you're multiplying all that by 7. That's the route that I took. I did 50 times 7 and then just subtracted 7. Right? Real easy way to do multiplications. Try and write it in terms of sums of powers of 10.
So now you can do that thing.
Right now, the numerator is difference of logs. The denominator is a sum of logs. So it's the product. 5 times 343. No, 5 times 300 is 1500. What's 5 times 40? 200? So we have 1700 right now. And 5 times 3? 1715. 343 times 5, 1715.
Oh, you did 43 times 5 and then 5 minus 3?
I did 300 times 5, plus 40 times 5, plus 3 times 5. Right, always writing in powers of 10 and adding them. That's the easiest way to do multiplication like that. That's only works if one of your terms is unitary. So it only has the units, the ones digit. If it's like 100 times 15, it doesn't work quite as nicely. Now I can do change of base. Because both numerator and denominator have the same base, we can just write this as a single logarithm. The base of our new log, remember, is what we're taking the log of in the denominator, 1715 in this case. And then of what we're taking the log of in the numerator. And so again, either of those answers, depending on how far you want to go. And if you go the route of simplifying it, you'll always get that answer, log base 1715 of 625 over 7, regardless of the original base. Right? Otherwise, it's always going to look like that, just possibly a different base. Right? If you did log base 5, those would all just be log base 5 instead. If you did log base 11, they'd all just be log base 11 instead. But the process is the same, and your answer is going to be the exact same form.
Log 1.
What do you mean log 1?
You could take the log of 1.
What base do you want to use?
Oh, I meant that base.
1 is not a base.
But wouldn't that get rid of the 1 though?
I don't think it's gonna get rid of that 1. Remember, for bases, it's not 0 and not 1. It's greater than 0, not 1.
And log 2? Or base 2?
So log base 2 of 1 is going to be 0. In fact, log any base of 1 is 0. That's a problem. What do you do with the left-hand side?
Is undefined.
Is there any way to isolate the x out of that now?
Would it just be 0? You can distribute it.
There's no way to distribute that log through. You could do it if it was a product or a quotient, right? Then you can use log, but there is no simplification for log of a difference. So that is a problem. That's going to get us right back to where we started, by the way. Log base 2 of anything being 0 means that whatever you're taking log of has to be 1, which gets us right back to the original equation. So something like this. This one, luckily, is nice enough that we can do it by hand. A lot of the times, you're not going to be able to. In fact, a lot of exponential logarithmic equations can't be solved analytically. You have to solve it numerically. But that's a topic for a different course. Factor out the smallest power. X versus negative x, which is smaller.
Negative.
It would actually depend on x, but we're going to say negative x. When you factor out 2 to the negative x from 2 to the x, what are you left with?
Negative.
And so remember, factoring is the opposite of distribution. So when you factor something out, you're dividing, right? 2 to the x divided by 2 to the negative x.
1.
What do you do to the exponents when you divide same base? What was that rule?
Just 2. That's like going 2 to the power of x over 2 negative.
Right. So when you divide same base, what do you do with the exponents?
Get rid of it. They become 1. And 0. You put them over each other. X over negative x. Oh, yeah.
Subtract exponents. it's 2 to the x over 2 to the negative x. It's 2 to the x minus negative x, which is what? 2x. And of course, you're factoring 2 to the negative x out of 2 to the negative x, you're left with 1. Multiply both sides by 2 to the x. Then move everything to the left-hand side and leave the right-hand side as 0. Let's make it even more obvious. Two to the 2x is not the same as 2 to the x all squared. That's quadratic form. What you would really do at this point is do what's known as a change of variable. Let's just use y. Let y be 2 to the x. And that's what our equation would become. Y squared minus y minus 1 equals 0.
And that would be right.
Well, we're not done yet. We have to solve it. How do you solve quadratics?
What's our formula?
This can't be factored, so you have to use quadratic formula.
What's our minus b? Or what's minus?
You put plus or minus in the wrong spot.
Minus.
Negative b
Negative b.
plus or minus square root of b squared minus 4ac. A is 1, c is negative 1. I'm just going to write that as plus 4.
Over negative 2.
Over 2a. One plus or minus root 5 all over 2. But y we said is 2 to the x. Root 5 larger than 1 or smaller than 1? It's larger than 1. That would make 1 minus root 5 over 2 negative, right? Can 2 to the x ever be negative?
Yeah. Because it equals y.
What power can you raise 2 to get negative?
An odd number? An odd negative number?
2 to the negative 3. 1 over 2 cubed, which is 1/8. Again, what's the range of the exponential function? It's 0 to infinity. Positive, real numbers. 2 to the x is never negative. That leaves only one possible solution. 2 to the x is 1 plus root 5 over 2. What's that number?
Can we get rid of the 2's?
I'm just asking right now, what is that number?
Y.
Start of the semester, I mentioned it the very first day.
A relation?
Just that number. What is that number called? He was paying attention on the first day. It's my favorite number.
It's like a perfect square. Perfect summer.
It's my favorite number. It's the golden ratio.
It's a 1, 2, 5 thing. Now I know what you mean because it's something that works like perfectly.
Now, golden ratio is just the limit of the sequence of Fibonacci numbers. The ratio of the Fibonacci numbers. Take the n plus 1 Fibonacci number over the n Fibonacci number, they converge to the golden ratio. It's the most beautiful number in the universe because it's everywhere.
Infinity?
Not that number, I think. It's the most beautiful number in the universe.
I've never seen that number before.
You weren't paying attention on day one. It was on the day one slides. Put my favorite number and my favorite equation up there.
Oh yeah.
I'll be impressed if you remember the equation. Because even I can't remember, I have to look it up every time. Now you have an exponential function equals a number, so you just take a log of both sides. Why not take log base 2? together. That would be our solution.
So what's called the number? What's called the number?
Oh, that number, I don't know what that is. That's just log of the golden ratio. Because you could call it a logarithmic scale of the golden ratio. Speaking of log scales, those are actually very common, especially in statistics. When your data set is extremely large, when I mean the values in the data set are extremely large, you typically do what's known as a log scale to bring them down. And so you just scale them down. It makes it easier to work with.
Sorry, can you go back for a second? Thank you.
Equations involving logs start off the same way as with exponentials generally. You want to look to see if it's log equals a log, which in this case it's not. Right, if that was, let's say, a log base 2 of 5 instead, then you just set 3x minus 4 equal to 5 and you're done. And then solve that way. Sadly, that's not what we can do here. Well, what was the inverse of a log? How would you undo a logarithm? What's the inverse function of a logarithm? Exponential. We want to get rid of log base 2, so what should the base of our exponential be?
Log base 2.
What's the base of the log?
2.
So what should the base of our exponential be?
2.
So you take each side as an exponential base 2. The whole point of that was to get rid of the logarithm. You're left with 3x minus 4. What's 2 to the 5th power?
Two.
2 to the 5th, 32. And now we're back at just a simple linear equation. And 4. Divide 3. Single solution, 12. There is one additional step that you must now take.
Plug it back in.
It doesn't really play a huge role in equations like this, because we didn't really do anything fancy. But the logarithm now is a restricted domain.
That's 12.
right? You can't take the log of 0 or less. So what you actually have to do is just make sure 12 is actually in the domain, which it is. 3 times 12 minus 4 is not non-positive, so you're fine. Okay, so again, we now have a sum of logs. We can't, well, I guess we could technically. We could jump right to the exponential. And then use properties of exponents. I'm going to start with properties of logs.
It's like log x over log.
Right, sum of logs, log of the product. Just do that, shoot that x through. What's the base?
10. Right?
Oh, this one's tough. What's 10 to the first power? Oh, that was hard. I think we'll just leave that one there. X squared plus 3x equals 10.
Then minus 10 is a quadratic and the quadratic 1.
This is now a polynomial equals something, and it doesn't matter what degree the polynomial is. It's always the same way. You always get everything on the one side equals 0. Can that be factored?
Yeah.
What's it factored to?
That I don't know.
5 minus 2 is 3. The 5 has to be positive. Right. Solving that quadratic, you're going to get either -5 or 2. Again, we were dealing with logarithms. So you have to check each one. Can -5 be a solution?
We have to plug it back in or no?
I mean, kind of, but not really.
And it can't be negative.
Can't be negative, right?
So it's not
-5 can't be a solution. If it was, you'd have log of -5, which you can't have. By the way, it's also not in the domain of the other one. -5 plus 3 is -2. That also clearly doesn't work. So -5 is out. What about 2? Can 2 be a solution?
Yeah.
Yes. So your solution set is just 2. Write this because -5 non-domain log of x.
When's our next test?
2.
That's gonna be like our midterm one.
Just a second there. But I'll discuss it as we get closer. Okay. GPT, do your thing. start with this one. So
Base 3.
let's do a different approach for this one than what we did for the one that involved 2 to the x. Let's immediately jump to a change of variable. And say let y be 3 to the x.
So you have 1 minus 1.
If 3 to the x is y, 3 to the negative x.
1.
Would be y to the minus 1, right? Which is 1 over y.
Plus on both sides. Plus 1 on both sides. Or
Uh,
minus?
not yet.
Take base 10.
Multiply through by y. Get rid of the fraction. And there are actually 2 ways to proceed. The first is to write the left-hand side as a single fraction, and then you do cross multiplication, which is going to give you the exact same thing as just clearing out the fraction to begin with. All right, so we multiply by the LCD, which is y. And then subtract 10y. Now quadratic form. That does not look like it can be factored. Negative 10, or negative 10, plus or minus the square root, negative 10 squared, minus 4 times 1 times 1, all over 2 times 1. I think 96 is 4 times 29.
So
No, it's not 4 times 29. 4 times 24. Oh, and then 24 is 4 times 6.
4 squared. 4 squared.
So it'd be 4 squared times 6.
Square root of 6. Or no square root of 6?
And then just divide through by 2. 5 plus or minus 2 root 6. Okay, here's the question. Root 6 times 2, is that larger than 5?
No.
Square root of 6, is that larger than 2.5?
Yeah. It's gonna be like
It is not.
No.
It is slightly under 2.5,
2.45.
which means 5 minus 2 root 6 is still positive. So they are both solutions.
So if it's positive, or no, if it's greater than it, it's a solution, but if it's not greater than it,
Right, because remember, exponential cannot give you anything 0 or less. And 3 to the x would be one of those two values, which means x is log base 3 of one of those two values. And here we truly do have two solutions. You say this one's challenging, but okay. Same kind of situations we had before. You don't have a common base. Choose any base. Take the log. And then use your properties of logarithms. Distribute everything through. Move all of your x terms to one side, all other terms to the other. Don't like that both of them negative. What I'm going to do, because I don't like that both of the terms on the right are negative, is just multiply a -1 through.
Oh, I thought you were gonna take it out. You can't take it out.
I could. But I'd still have that negative that I can get rid of. So I'll just multiply everything by -1. Now factor out that x. And we can divide by that log 5 minus log 2. I think what I'll do is just keep going, and I'll try and write this as a single log. Numerator, we had that 2 log 5, so we can use the power law. Log of 5 squared. Denominator is difference of logs, that's the quotient. Then you have the product in the numerator, it's the sum of logs. And then change of base formula. Log base 5/2 of 50. I think that's how I'll write the solution. This one. On the left-hand side, we use laws of logs. You have a difference of logs, so you use the quotient law, right? Well, now look. On both sides, it's a natural log, right? What you're taking the log of has to be the same. So we can just say that 2x plus 1 over x minus 2 has to be 3. That is now a rational equation, an equation involving rational functions. Best way to solve these, multiply through by your LCD, which in this case is x minus 2. Now it's just a simple linear equation. Add 6 to both sides, subtract 2x from both sides. X equals 7. Now just check. 2 times 7 plus 1, that's positive. No problem there. 7 minus 2, that's positive. No problem there. Seven is indeed a solution. Similar to one we already did, actually. Except it's now x minus 3 instead of x plus 3. Again, start by using laws of logarithms to write the left-hand side as a single log. I'll just go ahead and distribute that out. What's the base? Take both sides as exponential base 10. This gives us x squared minus 3x is equal to 10. We now have a quadratic equation. That can be factored.
5, 2.
This time it'll be x minus 5 times x plus 2. This gives the two solutions, either x is 5 or x is negative 2. And now just check each one. Can 5 be a solution? Yes, that's fine, right? It doesn't make what you're taking a log of negative. Negative 2, right away, can't be. So we only have one solution, 5. Let's say, because -2 is not in the domain of log of x. So yeah, keep in mind now, when you're dealing with logs, you now have a restricted domain. It's kind of the first time you've had to deal with that. Second, well, actually it is the second time. The first time is when you were solving rational equations back in algebra. I had to make sure that your solution didn't give you a 0 in the denominator. It's the same kind of idea here. You now just have to make sure that your solution actually falls in the domain of every function involved. Otherwise, it's pretty much the same stuff as what you did in algebra. Any questions? So don't leave just yet. I'll put that up on the screen. You do have 2 things coming due on Wednesday. And then the equations homework will be due next Monday. So singles is with the last one. You can write anything you want on here. Double-sided. The only restriction is it has to be handwritten. It can't be typed out. You'll be able to bring this into the exam, which is in 2 weeks. Next Monday, it's the Monday after that. Do not lose them. You're not going to get another one. So make sure it's in a nice, safe location.